The subject of this video is topicity, and my real advice for you is this should be done entirely by building with your model kits as opposed to just trying to do it on paper. There are very few people I've found who can do this particular exercise on paper. In fact, I'm not one of them. If I want to figure out whether a molecule has homotopic, enantiotopic, or diastereotopic protons, the fastest way for me to do it is to build a model and then actually physically manipulate things. What you need to know is that there are basically three interesting types of topicity problems. You draw out or build a molecule and you designate the hydrogens you're interested in as HA or HB. And then what you do is you replace HA with X and HB with X and see what the result is. X in this case is probably deuterium for the purposes of figuring out what the stereogenic centers are. It doesn't really matter, but the point is that you will actually go ahead and make these things, or at least very least draw them both out, and then decide what the difference is between the molecules. Homotopic protons are ones where if you replace HA with X and HB with X, you will end up with two molecules that are identical, the same. Enantiotopic protons, of course, if you replace HA with X and HB with X, the molecules that result are mirror images that aren't superimposable. They are enantiomers. Whereas, if you have diastereotopic protons, then when you replace HA with X and HB with X, the molecules that you get out the other side are diastereomers. They won't be mirror images at all. So we'll start with something that's very easy. Let's imagine we have an ethyl group, and on that ethyl we have a HA and a HB. Then what is the relationship between those two hydrogens? Well, you replace HA with an X, and what you get is ethyl X. You replace HB with an X, and what you get is ethyl X. You can rotate this and put it on top. The red and the blue don't matter, and what you have is ethyl X, so the molecules are the same. Again, this seems trivial, and it kind of is. Let me show you a better way of approaching this problem, and that is by actually building the models and then doing the replacement. So you can see I have two ethyl groups lying there. This is HA on the one ethyl group. That is HA on the other ethyl group. Meanwhile, HB is right there. HB is right there. The idea is that you're going to build two exact copies of the molecule in question, and then you're going to substitute for HA and HB. Notice I have now substituted X, which is the screen ball, for HA. I have substituted X, which is the screen ball, for HB. And then the question is, what is the relationship of the two molecules in question? And the answer, of course, is that they are identical. They are mirror images and superimposable. They are identical. For an example of enantiotopic hydrogens, enantiotopic protons, let's consider isopropanol, and let's replace HA on the left and HB on the right. Again, I strongly advise you to do this with the model kit, but even if you're doing it on paper, what you can then do is just substitute in X for HA and X for HB. Again, the right way to solve a topicity problem is to build both models and then to compare the models to each other. So here, we're trying to decide between HA and HB on isopropanol, where HA is this proton and HB is this one. Likewise, HB, HA. So again, what you do is you build two copies of isopropanol, and then you substitute X, put a green ball on HA. Likewise, at the same time, what we're going to do is substitute and put a green ball on HB. And you do that again with two different copies of the model so that you can then decide what the relationship is of the two molecules once you have finished. So you can clearly see that these two molecules are mirror images of each other. The oxygens face each other, then these two green balls are facing each other. And likewise, you cannot superimpose them. If I make the two red items match up, you can see that the green balls are on opposite side of the molecule. If instead I make the green balls match up, then the oxygens are on the opposite side. Said another way, I have non-superimposable mirror images. Those guys are enantiomers. Once you have substituted in X for HA, I assume you can assign the stereochemistry for this molecule easily enough and identify that it is in fact the S enantiomer of this alcohol. Meanwhile, if you substitute in X for HB, you have the R enantiomer of the alcohol that results. So these two are enantiomers. Once again, I find this easier to do with the model kit in my hands as opposed to on paper, but it can be done on paper. Finally, diastereotopic protons are ones that result essentially when you put an X on and it creates two new stereogenic centers, the one that you are altering and one that was already there, or a prochiral spot that was already there. So if you already have a stereogenic center, then it's fairly likely that you can create diastereotopic protons, but if you have a center that could be stereogenic and isn't yet a prochiral center, then also you can get diastereotopic protons. For example, we have cyclopentanol. Before we do a substitution of X for HA or HB, this molecule has a plane of symmetry running right down the middle. However, as soon as we install something, over here, anything, it will create two new stereogenic centers, the one that results when you substitute for HA or HB, and as soon as you do that, it breaks the plane of symmetry and creates another stereogenic center where the oxygen is. This carbon, at the moment, has two of the same groups coming off of it. It is only prochiral. It is not yet chiral, but will become chiral if you do something to disrupt the symmetry. This then will create diastereotopic protons. Once again, I find it easiest to do this with model kits in hand, but if you must, substitute X for HA, X for HB, and compare what results. Here, the comparison will be between two different cyclopentane molecules, and what we're going to compare is HA versus HB. So once again, you build two identical cyclopentyl alcohol molecules, and then you go ahead and substitute a green ball, or X, for HA and for HB. It's actually easiest, I think, to see that these are diastereomers if you think in terms of which stereogenic centers have stayed the same and which stereogenic centers have changed. Specifically, the stereogenic center that is now defined by the alcohol is facing us as opposed to back away from us in both cases. So that stereogenic center has remained the same, whereas the new stereogenic center created by X has now flipped. This X is coming toward us, that X is going away. So we have one stereogenic center that remains the same, the alcohol, and one stereogenic center that has flipped, which is to say, the X's. Therefore, these two molecules are diastereomers of each other, and the hydrogens, HA and HB, are diastereotopic. Once we have installed an X for HA, that creates a new stereogenic center, which is R. But at the same time, it makes the OH now stereogenic as well, and that is an S stereoisomer. If instead we substitute HB for X, the OH is still S, so that stereocenter remains the same, but the new stereogenic center, created where the X is now S. So this stereogenic center has flipped. Said another way, these two molecules are diastereomers. Or perhaps another way of thinking about it is they are not mirror images of each other. They are different molecules altogether, and yet they cannot be superimposed. But my personal preference for describing diastereomers is at least one stereogenic center remaining the same, the alcohol as an S stereogenic center, and one being different, flipped, the X stereogenic center, which goes from R to S. And again, the kind of system that gives rise to diastereotopic protons is where you either have a chiral center already, or you have a prochiral center, such that when you do a substitution, this becomes chiral. Either way, you will end up with diastereotopic protons. The moral of the story for topicity is to build two exact replicas of the molecule in question, and then substitute a ball for HA and a ball for HB and compare them. You can do this on paper. It's easier to do with the model.